So there's a couple things we're going to work on in section 1.3. We're going to work on sets of numbers. We're also going to work on understanding less than, greater than, or equal to signs. First things first, though, let's start with problem number 24. They ask you for a decimal equivalent to 2/3. So to find a decimal here, what you can do is start by dividing the numerator by the denominator. 3 into 2. And you don't get very far, do you? Well, 3 doesn't go into 2. So let's add a decimal point and then throw in a 0. Does 3 go into 20? How much? How many times? 6. Right? So we subtract and we get a 2. We put another 0. And you start feeling like you're a hamster on a wheel, right? Because you're going to get another 6, and then 18, and then a 2, etc. And it's just going to be 6s all the way down. Dot, 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 dot. Means it continues forever. There's actually some math notation for that. Have you seen this before? 0.6 with a bar. It means that that number or that part of this repeats itself, indefinitely. So it's kind of a clever little pattern here. Let's try a couple more that are like that, converting decimals into fractions, or fractions into decimals, I should say. So the next one I want to look at would be problem 26, part B. So let me dig that one out here for us. Actually, no, I said it right. We're actually going to go the other direction. Well, not quite. 26b gives us this number, 0.2444, etc. So the 4 part is repeating. If you're going to write it with this fancy notation, it'd be 0.24 and then a bar over just the 4. And let's do one last one. Part D. 0.456, 456, 456, etc. Try and write that one using that bar notation. Yeah, there's going to be 3 characters underneath that bar because the whole pattern 4, 5, 6 repeats itself. By the way, if you were to ever take out a calculator and have around fun with this one, 1/81st has kind of a neat pattern. 0.0123456789 bar. So kind of an interesting one on that end. All right, some useless trivia for you to amaze your friends with. Let's understand a little bit more about these kinds of numbers. Numbers where you have this repeating pattern or they can be written as a fraction are called rational numbers. And they're one of 4 different sets of numbers that we can work with. So the basic set of numbers that people started out with are called your counting numbers. And those would be things like 1, 2, 3, 4, 5, etc. If you add the number 0, you get another set called whole numbers. If you have to borrow money or borrow in some way or another, if you end up with negative numbers, then the negative numbers and the whole numbers give you the integers. And that's where we're going to start out. This is the first set that I want you to know by name, is integers. What would be some other examples of integers? Not just -5 and 5, but some big numbers. What would be another example of an integer? 1,000? Sure. 1,000. Trying to remember who it was. I was hearing about some football players. No, how much does Stafford make a year? 20 million. All right, so 20 million. There's a nice big integer for you. The thing about integers is that there's no decimals and no fractions. So they're the kinds of answers that you want on an exam. Rational numbers. The word ratio means something compared to something else or something over something else. So these are your fractions. Now they don't have to just include fractions. The number 4 can be thought of as a rational number. So anything which is an integer is also automatically a rational number. But they can be more general too. They can be decimals like this, that end, or repeating decimals, like some of the examples we just dealt with, 0.456 bar. As long as it can be written as a fraction in one way or another, it's an integer, or it's a rational number. Irrational numbers are kind of your oddballs. They're numbers that, if you look at their decimal, they never repeat and they never end. In fact, sometime during the semester, I think it's, I'm not sure, but I think it might be a Monday this year. Maybe a Tuesday. We're going to run across Pi Day. What's Pi Day going to be? When's that going to be? March 14th. Although I heard in France they celebrate it in like October or November, because it's the 314th day of the year. Whatever. Yeah. All right. I like our ways. So let's work through and understand what I would ask in a problem like this. There we go. So let me give you a set of numbers. And to denote a set, we're going to use this curly brace. So numbers like 67, 4 over 13, negative 5.9, 11 and 2/3, square root of 2, 0, 3, and negative pi. What I'd first like us to identify are the integers. What are the nice even numbers in this set? Justin, you want to take a stab at that? What are the even numbers? Yeah, nice. The integers. So they don't have any fractions or decimals. 67, 0, and 3. Good. So 67, 0, and 3. Now the next set I want to look at are the rational numbers. Now the rational numbers is a little bit bigger set, but rational numbers also include the integers. So if you're an integer, you should also be in this set, 0, 3, and 67. Let's think about what else we should add. You want to add fractions and or anything that can be written as fractions. So 4 over 13, negative 5.9, 11 and 2/3. So let's add those to our set. 4/13, negative 5.9, and 11 and 2/3. Now there's the rational numbers and then the irrational numbers. There's no overlap between these two. You're one or the other. The rational side of the argument, that's you. The irrational side of the argument, that's the other person, right? So there's one or the other. It's not both. What haven't I used out of my set? Square root of 2 and negative pi. So square root of 2 and negative pi. Now if you combine these, if you take and put this and this together, you get what's called the real numbers. And basically that's just all of the above. All of the above numbers. So everything here is a real number. It's not till math 1150 that you're going to see something that's not a real number. And we'll kind of dance around it a little bit in this course, but not too much. Okay, let me give you one more like this, and then we'll finish up section 1.3 pretty quickly after that. Is there anything specific on this one before we do another example? This is exactly how I want you to work these problems on an exam. This is exactly what you're going to see. Probably be the very first problem on your exam. Let me give you another set, and let's go through this. Try and be an active participant this time. -7, -11 over 8, -1, 0, square root of 2, pi, 4, 5.111, and 11 2/5. So I want to identify the same 4 sets of numbers: integers, rationals, irrationals, and the reals. So what are those 4 sets of numbers? I'll give you a second or two to look at those. Try and decide some of that yourself first. Okay, so what are the integers here? Good. So the integers would be -7, 0, and 4. Oh yeah, -1 too. Thank you. Missed one. All right, good. Now, as far as the rationals are concerned, these are also rationals, so those should be included on our list. So -7, -1, 0, and 4. But what else can I include now that I've expanded to rationals? Good? Good? One more. There we go. Perfect. So these are all rationals. -11 eighths, 5.111, and 11 2/5. Cool. Now what's gotten left off? What haven't we used? Square root of 2 and pi. Those are your irrationals. Those are pretty strange numbers. They never end. They never even repeat. So square root of 2 and pi. Those are your irrationals. Now when you put those all together, everything here is a real number. So all of the above numbers are real numbers. The above numbers are real numbers. Basically all the above. Cool. All right. There's a few more examples. You should do these for homework. These are on your handout, but they don't have problems quite like this in the book. They have stuff that's similar. So just make sure you do these problems as part of your homework. It'll help you out for your exam. Okay, a couple last things to finish up for this section. First things first is a less than or greater than signs. So I get embarrassed about saying it, but it does seem to help people sometimes. When you're trying to decide less than or greater than, keep in mind that the alligator eats the bigger number. So the bigger number should be on this side of your inequality. For instance, problem number 40. 898 and 889. Which one's bigger? First one or the second one? First one. So that's going to have the bigger side. Like that. Well, that one's kind of like a nice warm-up toss. Let's look at some that are maybe a little bit more thought-provoking. Starting with problem number 44. Negative 19 and 2/3 and negative 19 and 1/3. So, what I suggest you keep in mind is that smaller numbers are to the left. So let me start out by putting a 0 here. And as I move out the number line to the left of 0, which one of these am I going to run into first? Am I going to run into negative 19 and 1/3 or negative 19 and 2/3? Negative 19 and 1/3, and then further to the left would be negative 19 and 2/3. So what inequality sign am I going to put in here? Less than or greater than? There you go. Yeah, there you go. Less than. Thank you. All right, it's all right. I go through the same thing. I definitely feel your pain. So this is less than this because it's further to the left. All right, a couple more for you to try. Problems 42, negative 5 and negative 4, and 46. Negative 2.27 and negative 5.25. So just a couple to think about real quick. There's a point here. So it's negative, it's negative 5. Okay. Mariana, how about the first one? Less than or greater than? Is she right? Yes, good. Less than. Cool, thank you. Christopher, how about the one below that? Nice. If you look out the number line, this one will be further to the left than this one. Thank you both. Let's add to this a little bit. Less than, greater than, or equal to. I'll do a last couple here, and we'll finish up with the absolute value. Problem number 70 gives you 0.08 and 0.079. 72, 5.5 and 5 1/2. And finally, 80 is the square root of 2 and pi. So let's figure out what signs we're going to put in between each of these. is a little bit of a help. Oops. It's a 5. 5.5. Yeah, sorry about that. Now, it can help you out a little bit if you maybe to add a 0 here. That way both of these are 3 digits to the right of the decimal. You've got 0.080 and 0.079. So maybe that helps, maybe it doesn't, not sure. But you're free to do that. Ben, start us out, please. What inequality or equal sign should I put here? Good. Greater than. You've got basically 80 1,000ths is bigger than 79 1,000ths. Cool. Brooke, how about the next one, please? Good. Yeah, equal to. Good. 5.5 and 5.5. Anyone for the last one? Problem number 80? Square root of 2 is about 1.414. We just went over pi. 3.14925. Sorry about that. So, which inequality should I use here? Less than. By the way, this symbol, and I think it's one of your homework problems, kind of a squiggly equal sign is an approximation. So, square root of 2 is less than pi. Two last problems from this section. When you take the absolute value of a number, you're just going to get the positive part of a number. So for instance, the absolute value of 29 is just 29. Problem 66, the absolute value of negative 14 is just 14. That's it. For homework, there's a couple even numbered problems in here, but that's going to be the exception by far rather than the rule. So 4, 8, 9, 10, 11, skip up to 19 and 21, 27. Don't forget your handout. 33 through 47, 57 through 79. 83 can be kind of fun. If you wanted to play around with your iPhone, you can do something called a field test. Test the signal strength. So that'd be kind of cool. It's described in problem number 83. That's section 1.3. Correct.